Hello everyone, welcome back to Calculus BC. We are in lesson number 35 where we're talking about improper intervals. In the first two videos we talked about integrating functions that are to positive or negative infinity. So you'd see a positive or negative infinity right here. Both of these were negative infinity to positive infinity. Well, this video is going to show you when we also use improper integrals for numbers 0, 1, 0 to 2 or stuff like this. So if you look at example number 5, we're going to integrate from 0 to 1 of the function 1 over x. Well, you guys all know as well as I know that if you were to graph the function 1 over x, then it is actually undefined. It's actually undefined at 0. So I can't actually do an actual value for that here. So if I want to do this problem, well, we can use improper integrals. I can say, let's do the limit as g approaches. Now, in this case here, let's look at 0 from the right. Now, the reason why we're going 0 from the right is we're starting at 1. We're at 1, and we want the area, right, the rate of change up until we get to 0, but just to the right of that, right? Because this function is going to go really close to 0, but it never touches it. So 0 from the right. Again, because we're approaching from the right. We're at 1. And we're approaching it from the right. So that's why it's 0 to the right of our integral. And so we're going to replace, just like we've done before, 0 from the right with g. And then we're going to do 1 here of our function 1 over x dx. So what we're going to do now is what we've done in the first two videos. We're going to evaluate our integral. So we're going to write the limit as g approaches 0 from the right. The integration of 1 over x is the natural log of x. So this is going to be the natural log of the absolute value of x, evaluate it from 1 to g. And we're going to then substitute it. And so the limit as g approaches 0 from the right is going to be the limit of 1, the natural log of 1 minus the natural log of g. Natural log of g. And so for this particular example, we're going to say that the natural log of 1 is going to be 0 minus the natural log of 0 from the right. So that's really important. We're taking the natural log of 0 from the right. Well, as the limit, right? So the limit. So this actually becomes positive infinity. This goes to positive infinity. Again, this is very similar to like what we did with the L'Hopital stuff. Now, just like I said in the previous video, we have 0 minus infinity. So guys, this is not a number. This is not a number, so this actual particular example is going to diverge. So anytime you get positive or negative infinity in your actual answer, once you evaluate your limit, then it's going to diverge. So this one's going to diverge. Example number 6. If we look at this graph and we plug in 2, right, we plug in 2. We actually haven't looked at the graph. Let's look at the function actually. If we plug in 2 to our function, we're going to get 1 over the square root of 4 minus, well, 2 squared is 4, so I get 0. So again, I know that this is undefined at 2. Well, if I'm looking at 0 and I'm from 0 to 2, so here's 0 and here's 2, I'm approaching 2 from the left. So just like in this previous example, I want to go from the left. So the limit as h approaches 2 from the left of 0 to h. All right, and that's again how we figure that out, is that look at the other number and then go from that number to what's undefined and see which direction we're approaching it from. So again, 1 to 0 is approaching from the right, 0 to 2 is approaching it from the left. So that's probably the easiest way for me to tell you guys how to do that problem. And so we write our function down like we normally do, and we're going to integrate this. So this, again, is a refresher on how to integrate an arc sine function, because we have the square root of a number minus a function squared. So u squared is going to be x squared, a squared is going to be equal to 4. Remember, this does not have to be a perfect square for this to work. U is going to be equal to x, a is going to be equal to 2, and then du is going to be equal to 1 dx. So we're going to rewrite this as the limit as h approaches 2 from the left, and then I'm going to have this as our arc sine. It's going to be our arc sine from x over 2, and we're going to evaluate that from 0 to h. From 0 to h. And so let's actually go ahead and plug in what this value is. So the limit as h approaches 2 from the left, we're going to plug in arc sine of now 2 will be 2 from the left. Well, 2 from the left is going to just basically be 2 over 2 minus the arc sine of 0. The arc sine of 0. So based on what you guys remember from sine, or at least the value of sine, arc sine of 1, right, this ends up being 1, is going to end up being pi over 2, because the sine of pi over 2 is 1. The arc sine of 0 is just going to be 0, so this answer is going to be pi over 2. So when you do problems like this, again, you want to always look at the denominator and make sure that it's valid. If it's valid, great, do it like you normally would fundamental thermocalculus. Awesome. However, if one of the endpoints is not defined on this, but all the entire region is, then you're going to use this method right here. I say that because let's look down at example number 8 and show you guys this example. So if I look at this one from 0 to 3, well, this function is actually defined at 0. It's also defined at 3, but it's not defined at 1, which is in between 1 and 3. So then what you need to do is you actually need to split this up like we did in the last video, and we're going to say 0, and so at 1. Actually, let's do it this way. I need to do the limit. And I'm going to write big, so I'm going to use both of these for this. So for question number 8, I'm doing the whole space here. So the limit as, what letter am I on now? You'd think I would know this. So I'm going to do J, not I. So J approaches 1 from the left of 0 to J. And again, from 0, we approach 1 from the left-hand side. So 1 from the left of our function. dx over x minus 1 to the 2/3 power. And we're going to do plus the limit as jk. It's sad that I had to think for a second what the next letter was. K, 1 to the right, and this is going to be k to 3 of 1 over x minus 1 to the 2/3 power dx. And now what we need to do is just integrate. So we're going to do a little side note here for this. So when we integrate this, we would use u sub again. U would be x minus 1, du would be equal to 1 dx. And so we can just integrate the integration of 1 over u to the 2/3 power du. So I'm just integrating these two things over here as our side note. So this is going to be the integration of u to the negative 2/3 power du. And so when we integrate this, we're going to add 1 to the exponent. So we're going to get 1/3 here, and we're going to get 3 right there. So it's going to be 3u to the 1/3 power. So let's go back to our problem, and we're going to do the limit as j approaches 1 from the left of our function. And so we've already figured out what this is. This is going to be 3, and it's going to be x minus 1 to the 1/3 power. And we're going to evaluate that from 0 to j. And we're going to do plus the limit as k approaches 1 from the right of 3 times x minus 1 to the 1/3, evaluate it from k to 3, from k to 3. And we just start evaluating, and we want to make sure that we do not get any infinity problems right here. So since these are numbers, we can go ahead and plug these things in. So I can say, well, let's plug in j first. So 3, well, that's 1. And guys, remember that I'm plugging in 1. I should have said this up here when I plugged in 2, right? When I plugged in 2 here instead of 2 to the left. When we're looking at numbers, then the left-hand limit and the right-hand limit have to be equal to each other. Now, the reason why I didn't just plug in 1 up here is because the natural log of 1 does not exist. Natural log of 1 does not exist. But I can plug in the sine of 2. The sine of 2 is actually a value that exists. So here, I can just simply plug in 1. I get 1 minus 1, which is 0 to the 1/3 power, minus 3 times 0 minus 1 is a negative 1 to the 1/3 power, plus 3, again plug in 3 minus 1 to the 1/3 power, plus k, and again I can plug in k as being 1, as 1 minus 1 to the 1/3 power. So clearly these values are going to go away. This value is, well, I don't know why I erased that second one, I apologize. I meant to do this one. This one's going to go away. So we're going to be left with negative 3 times negative 1 to the 1/3 power, which is going to be 3. And then this is just going to be 3 times 2 to the 1/3 power. All right, it's not going to be something that I need to simplify a little bit. And that's really poorly written, so in that color. So I'm just going to write up here with all the words. So here we go with that problem. So that's what you need to do. So for this particular video, we talked about sometimes when you are integrating a function from negative infinity to positive infinity, that's a clear thing that it's in a proper integral. However, you have to also make sure that the bounds that I'm actually asking you guys to integrate from is defined. The function is defined on that interval. Again, if this problem had been -2 to +1, fundamental theorem of calculus. So you want to take that into account. If one of our endpoints makes the function undefined, then you're going to only do one limit. And again, you're looking at it from the left to the right. If it's in the region, if it's actually in the region of the function, then you will have to split it up for the bounds of the left-hand side and the bounds of the right-hand side. So I hope that makes sense. We're done with improper integrals, and I will see you guys in the next video. Take care.